You have heard me oops, sorry, I didn't mean to move that. Refer to Cartesian coordinates with another word this chapter. They're also called rectangular coordinates. Okay. So if you ever hear about like rectangular things, we mean x and y. If we're talking about Cartesian coordinates or Cartesian coordinate planes, it's also x and y. So it's just like your regular coordinate plane. So those things are x and y. And, like way back when you first learned about how to graph and plot points and things like that, you know that x is your horizontal movement or distance. And y is your vertical movement or distance. And I would say each of those are like directed distances, because if I give you a positive x, you move to the right, whereas if I give you a negative x, you move left. Same thing for y, up and down. We're going to start looking at what are called polar coordinates, and next week when we come back, we'll be doing polar graphs, okay, which are pretty neat. But polar coordinates come with an r and a theta. So r, like I like to think about r like it's a radius, okay? So it's some distance, okay? Instead of having an origin, we have something called a pole in polar coordinates, so it's like the center, sort of like the origin. And then you also have some angle. Now, when you're plotting rectangular versus polar coordinates, you usually see different versions of like a coordinate plane. So we're used to the rectangulars. We've got an x and we've got a y, and we've got the tick marks. And of course, if we were using graph paper, we would have the little square boxes, right? With the polar coordinates, you're going to see it on my next slide. You have concentric circles that represent different radii. So like r is your radius, it tells you which circle to go out to. And then you think about different angles. So a lot of times when you, like on your quizzes and stuff, you'll see like I have drawn in like the 45 degrees, and then you've got like your 30 and your 60. It gets really messy when you draw in all the lines. Sorry about that. But that's what the visual will look like as you're plotting polar coordinates. Now, if you could let those things fade away and you just think about it like what we have up here at the front where Eli was walking around, if you just think about it like four quadrants, we have points in the same location that can be written rectangularly, so x and y, but we could also name that point in a polar method with an r and a theta. Okay, so let's get into some specifics about the actual polar coordinates. Oops, we moved up. So polar coordinates, we've got our r and theta. I'm actually going to start with the theta and say a few words about theta. This is a directed angle. When I put that qualifier on, I did that with the parabola for P. I called it the directed distance from the center to the focus. When I put that qualifier of directed on there, it means the sign matters. So remember, like a positive angle will go counterclockwise, and a negative angle will go clockwise. Those things will happen from the same sort of like axis that we would see in chapter 4, the positive x-axis. Over here in this drawing, that center point, that's my pole. And so like my origin. And then instead of having like an X and a Y axis, you basically just have one you call the polar axis. Now you can think there is a vertical axis there. If you're on like pi half or 3 pi half, you have the vertical axis. But we start from the polar axis. So when we're graphing angles, if it's 120 degrees, we're going to start at the angle 0 over there to the right at the polar axis, and we're going to open up into the second quadrant area, 120 degrees. If it's negative, then we'll move clockwise around. Okay. R is also a directed distance. So when I say directed distance for R, it's in relation to your other part of your coordinate, your angle. If R is positive, you're going to move forward towards your angle. So like when we told Eli in that example, we said rotate negative 45 degrees, then walk forward 4 steps, and he got to the point. If R is negative, it means don't go towards your angle, go opposite your angle, so move backwards. Away from it. Mathematically, we would describe that like move in the opposite ray, move in the opposite direction, but basically go in the other direction. On the next slide, I'm going to give you 3 points that I want you to try to plot. Okay, so you understand R and theta and where you're going to plot them, and then I'll put my answers up in a little bit, and we'll clarify if we need to, any things we need to about directed angle, directed distance. So here are 3 points that I want you to plot. And if I were you, if I were drawing this in my notes, this is how I would do my polar system. And I don't mess around with like too many of the other lines. You can just have to see where those are. See if you can plot those 3 points. And I'm going to label them and color them. I'll call them A, B, and C. Okay, if I were plotting point A, I see that R is 2, so that means I'm on the circle with radius 2. And so the second circle out from the pole. And if I didn't have an angle, I'd just keep going around and around that circle. But since my angle is pi/3, it means at that angle, pi thirds, which would happen in that first quadrant, make an actual point. So I will go on the second circle at pi thirds. There's my point A. So now look at yours. Do you have yours in the right spot? Okay. The second one is B. Okay. Now notice that my R is bigger. It's 3, so I'm going to be on the next circle, the third circle. My angle is now negative. So that changes the direction that I move in my angle, right? Instead of going counterclockwise, I'm going to go clockwise, pi over 6. So I'm thinking about somewhere on this third circle, but if I go clockwise pi over 6, I'm just right below the polar axis. And so point B must be right about there. The last one, this is one you got to be careful of. You've got negative 3, 240. So really your radius, is a distance, so it's got to be positive. You're on the third circle again. The angle is 240, which I know that angle to be in what would look like the third quadrant over here, 240. But because the 3 is negative, I don't want to go towards 240. I want to move backwards on that angle. So rather than going forward 3 into the third quadrant, I'm going to go backward 3 into the first quadrant. So it's actually on the same angle as A. It's just on the next circle. How do we do? Got any questions, concerns? Yes.
Are we going to end up writing the points based on the photographs?
Yes.
How will we know when it's
You won't. So you would be able to write it multiple representations, which is going to be our next example. Usually I think the directions will ask you to keep theta within one revolution. So it could be one revolution positive from 0 to 2 pi, or you could really do one revolution negative. It might be easier, like when Eli was standing, to just say go negative 45. Okay, but we usually keep it just within one revolution as opposed to saying rotate 720 degrees. You know what I'm saying? Okay, any other questions? That's a good one, Ashley. Okay, so to address Ashley's question, here's our next example. We're going to plot this particular polar coordinate, 3, 4 pi over 3. And then you guys are going to try to come up with 3 other ways to write the same point. So I'm going to make a new polar grid. Like this. 3, 4 pi over 3. 4 pi over 3 is in the third quadrant. So out on positive R, so I'm going to go out 3 towards 5 or 4 pi over 3. Is it complete? Now, you have to stay within this restriction for me, negative 2 pi to positive 2 pi. But I want you to come up with 3 other ways to write the same point. So the R and the theta you give me get me back to 3, 4 pi over 3, but they don't look like 3, 4 pi over 3. So you can brainstorm with your pod mates how you're going to do that. Some of them come naturally to us, some of them maybe we'll have to think about. I get to the same point. There's treasure there. No. Changing degrees to radians will not count as a different way.
Oh, okay.
Okay, let's come together. David, does your group have any other representations that you could share with us? -3 pi thirds. Okay, so we'd still go out to the third circle, which, we should all have radius 3s. Because it's negative, we're going to move backwards from the angle pi thirds, which normally would be in the first quadrant, but if I go in the opposite direction, won't I land on 4 pi thirds? Yeah, that works. Okay. Noah, does your group have another one? 3 negative 2 pi thirds. So before we had a positive r and a positive angle, now we have a positive r and a negative angle. Instead of going all the way 4 pi thirds, let's take the shorter route and rotate -2 pi thirds. Okay, that's its like coterminal angle if you subtract 2 pi. So, and then if you go -2 pi thirds and walk forward 3, you land right there. I agree. So, one thing you can do if you're ever struggling to find like your missing point is pay attention. There's a pattern here. You should have a positive radius with a positive angle. Here we've got a negative radius with a positive angle. Then we have a positive radius with a negative angle, so now we need a negative radius with a negative angle. So we're going to have -3 and -5 pi over 3. I like doing it in radians as well because, like, notice your angles. You have one of all of the pi over 3s. Like, you don't ever repeat a 4 pi over 3 or a pi over 3. So it's kind of also a good indicator if you've got the right angles in there. You shouldn't, like, reuse pi over 3 as a positive or a negative. You should only have pi over 3 one time. So that's kind of handy. Okay, excellent. Moving right along. This part's pretty easy. It's just changing the coordinates from polar to rectangular or vice versa. So this is converting coordinates. After this, we're going to look at converting equations. That's the part on the homework that usually tends to be a little bit trickier for people. So I'm going to start with the type of coordinate that you know really well, which is an xy, rectangular coordinate. And I'm going to plot an xy point right there. So what does that mean? And think about how we had Eli moving around. It means go right x and up y. When we think about going from those rectangulars, xy's, into the polars, the r's and thetas, when you think about your r and theta, what shape are you going to be drawing? A right triangle. Okay. If we changed it and we said, instead, face forward on the polar axis, rotate through some angle theta, and then move forward r, we've just created our good old friend, the right triangle. So now the question is, if you know what x and y are, how will you get r and theta? Pythagorean theorem, excellent. Thank you, Eli. R squared equals x squared plus y squared. So make sure you got that down. That'll solve for r. How will you get theta?
Trigonometry.
Yes, trigonometry. Which trig function specifically, if you know x and y, will get you theta? Tangent, because that's opposite and adjacent. So we could say that the tangent of theta is equal to y over x. So if you know the rectangular coordinates, and you're trying to get the polar, the r and the theta, you're going to use Pythagorean and tangent. What are you going to be using to go the other way? If you've already used Pythagorean and tangent, what's left over? Sine and cosine. So if you have r and theta and you want to move into x and y, we've done this numerous times. The cosine of theta is x over r times by r. X equals r cosine theta. Y equals r sine theta. Sound familiar? Should be vectors. You can think about it like horizontal and vertical components force. We keep seeing the same things over and over again. Yes. Okay? Now let's do some conversions. If things are unit circle, please use your unit circle and do them exactly. If things are not unit circle, then use a calculator, right? Okay. Let's make this conversion. 1, -1 is in rectangular form. We are going to change it into polar coordinates. So we have x and y, and we want r and theta. Eli told me use Pythagorean theorem. R squared equals 1 squared plus -1 squared. That's going to be r equals the square root of 2. Got my r. Theta. The tangent of theta is equal to y over x, so -1 over 1. So we're saying the tangent of theta is equal to -1. What angles have tangents of 1 or -1? The 45-degree family, right? The pi over 4s are the ones with 1 and -1. And then you do have to be thoughtful here, just like we were in chapter 6. Where does the point 1, -1 exist? In the 4th quadrant. So Liam said -45 degrees. Would that map you there? Yeah. So we could put a -45 degrees. Or you could do the square root of 2 and 315. Or I suppose we could use 135 or what's the other one? 225, but then we would need a -r. You're probably going to land on one of the two with a positive r. Same thing. Cool, you're done. Okay, let's do one the other way. Oh, and I'm sorry, I meant to get rid of this thing because, of course, my thing is not. Hang on. My thing is way off to the side. So will you guys help me out when I get to that x? You see my cursor right over here?
Yes.
See right here? It's right here on the screen? Okay, now I'm going to go.
There.
Oh my gosh, you guys are so good.
Okay.
Wow. That is the best all morning.
Oh, there we go.
Okay, convert 2 power 4 into rectangular coordinates. So now this is polar, r and theta. And we want to turn it into x and y. This one's really pretty straightforward. X is r cosine theta. Plug them in, work it out. Y is r sine theta. Since these are unit circle angles, I know the sine and cosine of pi over 4, it's square root 2 over 2 for both. So that's 2 times square root 2 over 2. Which means my rectangular coordinates are square root 2, square root 2. So that's not too bad. The nice thing is if you learned that stuff in chapter 6, if you know the connections for those 4 equations over on the sideboard, then you have what you need. You're just reusing it, okay, in a different way. Okay. So here's the part of the homework that, like I'll say, give yourself a little bit of patience, let it be okay to not get the right answer right away. That's fine. You're just learning. I don't expect you to know how to do every single one right many equations, I can't tell you how to do every single one. So you just gotta like try some things and see what works. I do have up at the top of the screen some, like a pointer here. If you're being asked to take a polar equation and turn it into a rectangular, I'll say 95% of the time, once you get it in x's and y's, you want to solve for y. Don't we always see equations y equals for the most part? Now, of course I have this sometimes. Sometimes you'll solve for x because there is no y. If you don't have a y to solve for, then solve for x. And then other times you might have x squareds and y squareds, and those, like we're just coming off of conic sections, we know those might be circles, ellipses, or different conic sections. So sometimes x squared and y squared just kind of stay the same, and that's not correct. Okay, now these two that I have on the board I want to talk about just because you already know what shape they're going to be. If I tell you in polar system r is equal to 2, what would you graph? R equals 2. You would be drawing a, say it, you scared? R is always 2. You would be drawing a circle, right? Don't overthink that. If R is 2 and I give you no angle, then on that second ring, you just keep going around and around and around and you're drawing a circle. Okay, so we know it's going to be a circle. Now, you might know about the equation of a circle from geometry. That's one of those equations where x squared and y squared are on the same side. Okay, so I'm not going to solve for y on this one. Okay, if all you know is r is equal to 2, what's a connection from our 4 trig equations that will best be used to get x and y if all you know is r? Probably the first one, right? In order to sub in for r and make it x squared plus y squared, I need it to be r squared. What can I do to both sides of this equation? Square them. Square, square. This is r squared equals 4. And then x squared plus y squared is r squared, so I can now make my substitution with rectangular values. And oh yeah, I know that's the equation of a circle, so I don't have to keep solving. This circle has a center at 0, 0. R squared is equal to 4, therefore r is 2, so it's a circle with radius 2. That's the same circle you would have drawn in polar. Okay, they're the same thing. Okay, next one. If all I tell you in polar is that theta is pi over 3, what are you going to draw? A line. You don't know where on pi over 3 you're going to stop, right? You don't know if r is positive, so you should go towards pi over 3, or if r is negative, so you should go away from pi over 3. But we know this is a line. What does the equation of a line look like in rectangular form? Y equals mx plus b. Okay, so when I get to y equals mx plus b, I'll know I finished my equation. Okay, which one of these over on the side is going to help me most get to x and y if all I know is theta? Tangent. I don't want to use these two as sine and cosine because they have r's and thetas, and I've only got theta. So I'm going to write that down. Tangent theta equals y over x. And in this particular case, I've been told theta is pi over 3, so plug it in. The tangent of pi over 3 is equal to y over x. What is the tangent of pi over 3? Radical 3. Multiply both sides by x. Y equals the square root of 3 times x. That is the equation of a line. Mx plus b. B must be 0 because it's passing through the pole or the origin, and our slope is square root 3, which is square root 3 over 1. You know, if I were graphing that line, I'd actually probably prefer to graph the line theta equals pi thirds. That's easy, as opposed to graphing a slope of square root 3. Okay. We are also going to be asked to go the other way. So rectangular to polar equations. I want you to put as your goal for when you're writing a polar equation, we want it, if possible, to look like R equals. It's the same in polar as like Y equals in rectangular. That's like most of the time the equations look like R equals. Of course, if there is no R, you will have to settle for solving for theta. Then we'll end up being a lot. Okay. X squared plus Y squared equals 25. You're just going to start with a straight up substitution, right? X squared plus Y squared is really R squared. So make a substitution. R squared equals 25. Is that an acceptable answer for polar? No, because we want to solve for R. So square root of both sides, R equals 5. Now on this one, I don't actually have to put like the plus or minus because in polar, the radius is 5. We're drawing the whole circle. I don't need the negative 5. Okay, so if you think about it, it makes sense. You don't need the plus or minus anymore. Okay, x equals negative 4. Looking at your equation, what substitution are you going to make? X equals R cosine theta. Sub it in. R cosine theta equals negative 4. You just gotta look like you're trying to get rid of x and have r's and thetas. So use that substitution. Solve for r. So this is r equals negative 4 divided by cosine theta. If you divide by cosine theta, what are you multiplying by? It's reciprocal, secant theta. That's it. And that's kind of nice to know, like that last one comes out to be negative 4 secant theta because I had some other examples for polar to rectangular. Like if you have r equals 2 secant theta, you might be like, oh, none of these work. But if you rewrite it as r equals 2 over cosine theta, then multiply both sides by cosine, this is x equals 2. This one doesn't work out like that, so this is like where, like, give yourself some grace and try some things. Okay, get creative. If I divide by sine, that's not helpful. I need r sine theta to be on the same side. So what you should actually do is multiply both sides by r. Then you have r squared equals 6r sine theta. This is x squared plus y squared, and this is 6y. So you can also introduce an r that you need. And you could really write this as like x squared plus y squared minus 6y equals 0. Either one of these is fine. You could complete the square and write the equation of the circle if you wanted to, but you don't have to.
Can I take a picture of it?
Mm-hmm.
Have a good day.
Yeah, thanks, you too.